Good morning, everyone.
Lord.
Good morning. So today we have a review session. I will go over the lecture notes will be covered in the exam, Unit 1 to Unit 5. And if you have any question while I'm explaining these 5 units, let me know. You can unmute yourself at any time and ask me your question. Okay. So the exam will be like multiple choice. There is no multiple choice question. The exam will be short answer, a calculation, drive the posterior, maximum likelihood, and these kind of things. So it will not have any multiple choice questions, but I will ask you to calculate something by R. Is but simple questions like 2 parts of one of the questions or something. So I'm planning to have something like 4 questions. Some of them have many parts, some of them are not, plus 1 bonus question. And I hope you do great in this exam. Okay. Any questions before I start?
Can you say again what we need to calculate in R?
Okay, you need to calculate in R. Like there are many things we covered by R. We cannot calculate by hand. Like you can find the credible set by R. You can find the probability of H0, probability of X1 by R. You can find the probability of the predicted probability of some value like Y star given in a star. And but I'm not going to ask you to graph something, but I'm going to ask you to calculate something by R because there are many things you cannot do by hand. But you can calculate the posterior mean, posterior mode, posterior variance, standard deviation, and these kind of things. You can calculate this one by hand. You can calculate Bayes factor by hand, but there are many things you cannot calculate by hand. You have to use R. So I want to make sure that, because if I didn't give you any question about R, maybe my students will not go over the R. I will not practice on R. So I want to make sure that you practice on R and you understand how to calculate some specific values like predictive probability, like credible set, like probability which is here, and see these kind of things. Okay. Does it answer your question?
Yes.
Okay. Any other questions?
Hi, Professor. So is it like we're free to use our and laptop for all questions, or just given ones?
Now, if I asked you to use R to calculate something, use R. But if I didn't ask, do not use R. Like, for example, if I asked you to calculate the mean, the posterior mean or posterior mode, posterior standard deviation, there is a function of R can calculate this one. But I want you to, if I asked you to calculate by hand, if I didn't say clearly use R, you have to calculate by hand. So you write down the formula, plug in the values, get the value.
Okay, got it. Thank you.
You are welcome. Any other questions? Okay, let me set up my computer and go over the 5 units. And I uploaded guidelines. You need to go over these guidelines because the guidelines have many good important information like what units will be covered, what homework will be covered, what in-class assignments will be covered. All the class assignments, the in-class or handouts will be covered, and the homework, the 3 homeworks, and the 5 units. So let me share the whiteboard. Do you see the whiteboard? Guys, do you see the whiteboard?
Yes.
Okay, good. So let's start by Unit 1. Unit 1 is Basics of Bayesian Statistics. Unit 1. Basics of Bayesian Statistics. In this unit, actually, Unit 1, we went over the differences between Bayesian and frequency approach. We went over many of them, like we went over differences between Bayesian approach and frequency approach in terms of the meaning of probability. Like the Bayesian approach use subjective probabilities for the prior distribution, but the meaning of the probability in the frequency approach is based on what will happen in the long run. And we talked about the difference between these two in terms of prior and data. Prior and data. The Bayesian approach uses the prior distribution and the data, but the frequency approach uses only the data. It doesn't use any kind of prior information or prior distributions. And also we talked about the difference between these two in terms of the point estimate or the point estimation. In frequency approach, they use only the data for estimation, but in Bayesian approach, use the information from the prior distribution and information from the likelihood, and they combine these two and get something called the posterior distribution, and use this posterior distribution to estimate or to get the point estimation. Like, for example, when you get the posterior distribution as beta, you use beta distribution to find the posterior mean, posterior mode, posterior variance, posterior standard deviation, using some kind of formula. But the posterior distribution in this case has much information compared to the likelihood, because we add information from the prior distribution plus the likelihood to get something called the posterior. So again, the points estimate in frequency approach is based on the data only, but the Bayesian approach based on the data and the prior. And also we talked about the differences in terms of the inference. Whatever you use frequency approach or the Bayesian approach, you get something called interval. We call it confidence interval in frequency approach. We call it credible set in Bayesian approach. And for testing, in testing, we covered the frequency approach, you use something called p-value. But in Bayesian approach, we calculate the probability of H0 given the data and the probability of H1 given the data, and we compare these two to take our decision. But in using confidence interval, this one is 95% confidence interval or 99% confidence interval in frequency approach. This one a little bit confused because the meaning of the 95% is not probability, it is confidence level. But whatever you use the frequency approach or Bayesian approach, you get lower limit and upper limit, but the meaning is different. In Bayesian approach, we say with probability 95 or with probability 99, the population proportion will be between these two values. But in frequency approach, we say with 95% confidence level or with 99% confidence level, the population proportion will be between these two values. The confidence level is not probability. 95% confidence level means if I selected all the possible samples and calculated all the possible confidence intervals, 95% of these confidence interval will contain the true mean, 5% will not contain the true mean. So the confidence interval is a little bit confused in frequency approach, but in Bayesian approach is straightforward. We use we say probability. Those are some of the differences between Bayesian approach and frequency approach, the ones you need to be familiar with. Anything I missed or anything you would like to ask about in Unit 1? Okay, let's go to Unit 2. Unit 2, it talks about the Bayes rule. Unit 2. Bayes rule. We covered the Bayes rule, which in general, the probability of the parameter you are interested in given the data, which is posterior distribution, proportional to the prior distribution times the likelihood. But we started this unit by talking about the marginal and conditional probability. Marginal and conditional probability. Marginal and conditional probability. If we have two events, one is A, one is B. The probability of A is called marginal probability. Probability of B is called the marginal probability. But the probability of A given B happened, this one is called the conditional probability. Or probability of B given A happened, this one is called the conditional probability. So we talked about the marginal probability, conditional probability, and then we talked about something called law of total probability. The law of total probability. Law of total probability says if you have many events like B1, B2, B3, B4 up to Bn, you have many events. And the union of these events is the sample space. The union of these events is the sample space S. So this one is B1, event B1, event B2, event B3, event B4, up to event Bn. And you know the probabilities of these events, and you have another event, is called A. This event has some intersection with each event of from B1 up to Bn. So this one is the intersection between A1, B1, A1, B2, A1, B3, A1, B4, A1, B up to A1, Bn. The probability of A, it is very clear that the probability of A equal this one plus this one plus this one plus this one. So each is the probability of the intersection. So the probability of A intercept B1 plus up to probability of A intercept Bn. These ones can be written as this joint probability. The first joint probability can be written as the probability of B1, because you know probability of B1 times the probability of A given B1, A given B1, plus up to the last one. This one is the probability of Bn times probability of A given Bn. So which one I should use to calculate the probability of A based on what is given? If what is available, if you have the probability, the joint probabilities, like the probability of A intercept B1, probability of A intercept B2, up to probability of A intercept Bn, you sum this one, give me the probability of A. Or maybe you have the joint probability, the marginal probability of B1, B2, B3, up to Bn, and you have the conditional probability A given B1, A given B2, up to A given Bn. Based on what is available, you calculate the probability of A. This one is called the law of total probability. And we use this law of total probability to calculate, to reverse one of these probabilities, one of these conditional probabilities. So maybe if I need to calculate the probability of Bi, any one of these B, given A. So this one, Bi given A, is one of the inverse of one of these ones. So this one equal what? This one equal the probability of Bi times the probability of A given Bi divided by the sum over all of them, the sum over the probability of AI, BI times the probability of A given BI, sum over I equal 1 up to n. This one actually is called the Bayes rule. So where is this Bayes rule? I haven't seen this one before. You have seen this one many, many times. This one can be written as the probability of BI given A proportional to the probability of BI times the probability of A given BI. This is the formula we use all the time. BI is the parameter you are interested in, and A is the data. So the probability of the parameter you are interested in given data proportional to the probability of the parameter you are interested in as a prior distribution times is the likelihood. So this one actually is the Bayes rule. This one is the Bayes rule. And we use this rule in unit 2 in two cases. The first case is for events, second case for random variable. So using the Bayes rule, we use this one in two cases, which we call the B is theta and A is the data. So we write it down as the probability of the parameter we are interested in given data proportional to the prior distribution of the parameter we are interested in times the likelihood of the parameter given data. So why you change this one from A given B to B given A? Because we assume we know A. So once you plug in A as a data, it will be a function of BI or theta in general. So this one is the Bayes rule, and we use this one in two cases in unit 2. We use this one to update some probabilities about nominal variable or discrete or categorical variable. If you remember, we have plus, C plus or C minus, have cancer, do not have cancer. And we updated every time we get a new information, you update, and until you get the posterior probability of C plus and the posterior probability of C minus to take a decision. And we use this rule actually also, so this one for events, and this one for discrete case. For discrete case, we used the Kasparov example that we have prior distribution for some possible values for pi. So pi, probability of pi may be 0.10, maybe 0.25, maybe 0.3, maybe 0.7, and we have the probability of these values. The probability that it is 0.10, 0.2, probability it is 0.25, 0.7, probability 0.3 is 0.1, probability of 0.7 is 0.1. The sum of these probabilities should be 1. This one is called the prior distribution, which is probability of theta or probability of pi in this case. Sorry, guys. So this one is the prior distribution, and then you multiply this one by the likelihood. How do I get the likelihood? Because number of times that Kasparov beat the computer follows binomial distribution. So you plug in the data in the binomial distribution, you get the likelihood. So using the likelihood, you can get the likelihood of 0.10, likelihood of 0.25, likelihood 0.3, 0.7, and so on. So you update the prior distribution by the likelihood, you get something called the posterior distribution, and then use posterior distribution to estimate the parameter. For example, pi hat equal pi hat is using the basic probabilities. It is the sum of the possible value, multiplication of the possible values of pi. Sorry, this one should remove this one. Sum of pi times the probability of pi given y. So you use the posterior probabilities. You multiply the posterior probabilities by the possible values of pi, you get the estimation of pi. So in Unit 2, we learned the basic stuff also about the Bayes rule. How we came up with the Bayes rule, how to use the Bayes rule for some events to update the probabilities about some events, or to update the probabilities of some specific values as a discrete variable. So this one is a discrete variable, this one is events. But in reality, the pi take many possible values, infinity number of possible values. So this one is not real case, like pi is 0.2, 0.25, 0.3, 0.7. This is not real case. A real case is pi can take any value within an interval between 0 and 1. So this is why in chapter 3, in unit 3, we started working with pi as a random variable in general, not discrete, is a continuous random variable. So this is what we cover in unit 2. You have any question? Okay, unit 3. Unit 3. This one is posterior distribution of pi. How do we get the posterior distribution of pi in general? Take any value within an interval between 0 and 1. So unit 3 is posterior distribution of pi, and pi is between 0 and 1. This is in reality. Pi can take any value within an interval from 0 to 1. So in this unit, we talked first about the kernel and normalizing constant, the idea of kernel and normalizing constant, because we are interested in kernel. We always look at the kernel. So when we multiply the likelihood by the prior distribution, we ignore all the constant and we look at the kernel. This is kernel of what? So this is why we covered the idea of the kernel and normalizing constant. And then we talked about the differences between informative prior and non-informative prior. And then we talked about the conjugate prior, non-conjugate prior. And then we talked about how do we get the posterior distribution under some prior distributions, and how do we use it for estimation. And then unit 5, how do we use it for inference. So let's start. So in this chapter, in this unit, we talked about the difference between kernel and normalizing constant. For example, if I have this function, probability of y given pi equal n choose y, pi to the power y, 1 minus pi to the power n minus y. What is the variable in this case? The variable is y. The first one is the variable y. So this function is a function of y, assuming we know pi. Given pi, it means pi is known. So anything is a function of y is apart from the kernel. Anything is not a function of y is apart from the normalizing constant. So this one is a function of y. So n choose y is apart from the kernel. Pi to the power y is a function of y. If I change y, this value will change. This one can be written as 1 minus pi to the power negative y. This one is a function of y times 1 minus pi to the power n. So this one, all these ones depend on y. So this one is kernel. And this one doesn't depend on y. This one is normalizing constant. So this is how I decide which one is normalizing constant, which one is kernel. Keep in your mind, if we know y and we don't know pi, this one is called likelihood. So L of pi given y this one equal. If this one is n, choose y, pi to the power y. 1 minus pi to the power n minus y. Assuming now we know pi, but we don't know pi. We know y, but we don't know pi. So now this one doesn't depend on pi. So this one is part from the normalizing constant. This one depends on pi. This one depends on pi. So this one is kernel. And this one is normalizing constant. When you write the range for y, for this one, the variable is y, and the range is 0, 1 to up to n. But for the likelihood in this case, because we assume pi is unknown, so the range of pi is from 0 to 1. So this is the idea of normalizing constant and kernel. So if I give you any function, or if you have any function, you can divide this function into two parts. Normalizing constant and kernel. Based on what? Based on the variable is what? Anything change when I change the variable, it is normal, it is kernel. Anything it doesn't change when I change the variable, it is part from the normalizing constant. So this is the first point we talked about. Second one, we talked about informative and non-informative prior. Informative and non-informative priors. If you use the prior distribution has some information about the parameter, it is called informative prior. If you use some prior distribution, it doesn't have any information, or it's a very small information about the population parameter you are interested in, it calls a non-informative prior. We covered many. For the non-informative prior, for example, we covered uniform 0, 1, which is equivalent to beta 1, 1. We covered another non-informative prior, which is Jeffreys prior. Jeffreys prior is beta half. We covered also, yesterday we covered the beta 0, 0, but this one is improper. This is why they changed this one to be beta some epsilon. This value is very small value. It's like Boyan 1, or Boyan 0, 1, some small value. All these ones are non-informative prior. So uniform 0, 1, which is beta 1, 1 is non-informative prior. Jeffreys prior is non-informative prior. Beta 0, 0, beta epsilon, and epsilon is a very small value. All these ones are non-informative prior. But for informative prior, we covered the sum. Informative prior. Informative prior, we covered the histogram prior, and also we covered discrete prior, and we covered the very famous one. We covered the beta, alpha, beta. This is informative prior. So if I use uniform, I multiply the likelihood by 1. If I use Jeffreys prior, I multiply likelihood by beta half. If I use beta 0, 0, I multiply by beta 0, 0. If I, which is beta 0, 0, which is its kernel as pi to the power negative 1 times 1 minus pi to the power negative 1. I multiply this one by the likelihood. Beta epsilon, Boyan 1, Boyan 0. It is, and all these ones are easy in terms of I don't need to select the parameters for the distribution I'm using. But if you use this one, beta, alpha, beta, you need to know how to select alpha and beta. How do I select alpha? How do I select beta? So there are many strategies to use to select alpha and beta. I will show you this one in a few minutes, but after I go over one more types of parameter Brier distributions, conjugate and non-conjugate, conjugate and non-conjugate, conjugate and non-conjugate priors. How do I know the prior is conjugate and the prior is not conjugate? See, when we find the posterior distribution, the probability of theta in general, or pi for our example, given y, proportional to the probability of theta or pi in our example times the likelihood of theta given y. You use some distribution for this one. If you use the distribution for this one and you found the posterior is the same distribution, so we call this one conjugate prior. So if you use the normal for this one and you found the posterior is normal, so normal is conjugate prior. If you use the uniform for this one and you found the posterior is uniform, so uniform is conjugate prior. If you use beta distribution for this one and you found the posterior is beta, it means beta is conjugate prior. Otherwise, it is non-conjugate prior. Otherwise, it is non-conjugate prior. So this is the difference between conjugate prior and non-conjugate prior. The conjugate can be informative, can be non-informative. The non-conjugate can be informative, can be non-informative. So there is a difference between informative, non-informative, and conjugate and non-conjugate. Informative means it has some information. Non-informative, it doesn't have information or very little information. Conjugate means posterior and prior are from the same family. Both are normal, both are beta, both are gamma, both and so on. Non-conjugate, it means they are from different distributions. One is normal, one is gamma, and so on. So how do I select alpha and beta? Because this is very important. Because I would like to add some information in the estimation and inference, plus the likelihood. So how do I select alpha and beta that match my belief or match some previous stat? So there are many strategies we cover. Guys, if you have any question at any time, please let me know. So we covered many methods, like so how do I select alpha and beta? By graphing many different ones and see which one match your belief, like graph. Many ones. Like the range of pi is from 0 to 1. Maybe you believe that the small values have higher probability compared to the bigger values. Maybe you believe that the value in the middle, which is 0.5, has the highest probability. And when you go to the right side or left side, the probability decreases. Or maybe you think all of them have the same likelihood or the same probability, but this is uniform, which is beta 1, 1. Maybe you think the highest values has higher probability and the smallest values has the smallest probability. So you can use this one. And when you graph this one, you know what alpha and beta you give to R to give you this one, and so on. But this one take much time and is not nice one. It take much time. So another method is maybe there is some previous study. So in the previous study, the sample size is selected and how many successes, how many failures in this previous study. So use alpha equal number of successes plus 1 and use beta equal number of failures plus 1. When you use this method, you will use a Brier distribution with alpha and beta, and this Brier has information equivalent to the information in the sample of the previous study. Because a sample of 100 has information more than a sample of 50. So this is how to quantify the information based on the sample size. So if you use alpha equal number of successes plus 1 and beta number of failures plus 1, it means you use a Brier distribution, has information, equivalent to the information that they in the previous study. Another method, one more method. You can have some, like maybe you as a researcher, you believe that the mean of the parameter, the mean of the population proportion is something like 0.3. And the median is something like 0.35. Those are two conditions. And keep in your mind, if this is your belief, like I believe the mean is 0.3 and the median is 0.35. You know the formula for the mean and you know the formula for median. The mean is alpha divided by alpha plus beta. Median is alpha minus 1/3 divided by alpha plus beta minus 2/3. So you solve this equation, you get alpha and beta that match your beliefs about the parameter. Or maybe you use another condition. There are many conditions. Like I would like to have the prior distribution. The mean of the prior distribution is 0.3 and the sample size is something like 30. So alpha plus beta minus 2 equal 30. So you solve this equation with this equation to get alpha and beta. So you can set two conditions. The two conditions are functions of alpha and beta, and you solve these two and you get alpha and beta. This is another method. One more method that you can graph many beta distributions. Each for each, you show the lower limit and upper limit of 95% probability. So you graph one, and this is the lower limit and upper limit, and in between 95%. Or this one is the another beta distribution, and the area in between is 0.95%. And then you select the one that match your belief based on, I think it is between these two values, I think it is between these two values, and so on. So there are many ways to select alpha and beta. Again, why you select alpha and beta? Because I need to have, if I use this method, if I assign prior distribution beta, I need to know what is alpha and beta in this prior distribution. So once you know the prior distribution and the likelihood, you multiply the likelihood by the prior distribution, you get something proportional to the posterior distribution. The multiplication would be a kernel of some specific distribution. So maybe this kernel is a kernel of normal distribution, maybe beta distribution, maybe gamma distribution, maybe exponential distribution, Poisson distribution, and so on. But once you know the posterior distribution is what, now you can do estimation and inference. Once you know the posterior distribution is what, now you can find you can do inference and estimation. So if you use the actual uniform, you use the Jeffreys prior, you use the beta 0, 0, you use beta epsilon, epsilon, you use beta alpha and beta. Under all these ones, the posterior distribution is beta also. We found the posterior distribution under all these ones, whatever you use uniform, Jeffreys prior, beta 0, 0, beta epsilon, epsilon, beta alpha and beta. Under all these ones, the posterior distribution is beta. Under all these ones, the posterior distribution is beta, alpha plus y, and beta plus n minus y. So this is the posterior distribution, which is alpha plus y and beta plus n minus 1. The first one is the alpha posterior, second one is beta posterior. So now I know the posterior distribution. Once you know the posterior distribution, now you can do estimation, now you can do inference. Like you can do estimation using the posterior mean, posterior median, posterior mode, and each has a formula. Maybe you would like to estimate pi by posterior mean. You know the formula: alpha divided by alpha plus beta, alpha posterior divided by alpha posterior plus beta posterior. Maybe you use the median to estimate pi. Maybe you use the mode to estimate the pi. This is the estimation. Maybe you'd like to estimate the posterior variance. This one has an estimation, has a formula as a function of alpha and beta, or alpha posterior, beta posterior. Or maybe you get the standard deviation, the posterior standard deviation. So all these ones are a function of alpha posterior, beta posterior. So once you get alpha posterior, beta posterior, you can do estimation. What about inference? How do I get credible set? How do I get the frequency approach? Credible set, and calculating the probability of H0, probability of H1. So this is unit 4. So unit 4 is estimation and inference about pi. In this one, we talked about the frequency approach and Bayesian approach. Frequency approach, Bayesian approach. Frequency approach, they estimate pi by the formula of y divided by n. And I showed you how they came up with this formula, y divided by n. This is the maximum likelihood estimation. And we went over the steps. The first step, find the likelihood. Second step, takes the log of the likelihood. Third step, takes the derivative of the log likelihood with respect to the parameter you are interested in. Fourth step, you set this one equal to 0. The log, the partial, or the derivative of the log likelihood with respect to the pi, set equal to 0, and then solve. You will find pi hat equal y divided by n. I showed you this one in lecture notes. This one is called maximum likelihood estimation. And also yesterday we practiced on another example that if the data follows Poisson distribution. This case, if the data follows binomial distribution. So you use the likelihood of binomial distribution, follow these steps, find the likelihood, log of likelihood, take the derivative with respect to pi, and then set equal 0, and then solve to find pi hat. This is a frequency approach estimation. And again, yesterday we went over if the data follows Poisson distribution, and we found lambda hat equal sum of y divided by n. This is the estimation of pi hat. But for Bayesian approach, you can use pi hat as median, mode, mean, or posterior mean, posterior mode, posterior mean, median, mode. It means there are 3 ways of estimation for the pi, but the frequency approach is only one method, which is y divided by n. And also we covered how to calculate the posterior variance, posterior standard deviation, and so on. So this one is called estimation. What about inference? Inference, still frequency approach. Inference, they use something called the confidence interval, which is, if you are interested in the formula, but it is not required in our course. Pi hat plus or minus z times the square root of pi hat times 1 minus pi hat divided by n. This is confidence interval with 95% or 99%. And how do I get these confidence interval? Use the function in binomial dot test in R, binomial dot test. But it's not required to use the formula in our lecture note, on our course. So this is confidence interval. Another type of inference is testing. They found something called p-value to test, for example, h0 pi is less than some specific values, let's say 0.2, pi versus h1, pi is less than 0.2. So they do not calculate the probability of h0, probability of h1, they calculate something called p-value. This function gave you the p-value, and based on the p-value, you take your decision. If it is less than alpha, you reject. If it is greater than alpha, you fail to reject. This is inference in frequency approach. What about inference in Bayesian approach? Inference in Bayesian approach depends on the posterior distribution. So how do I get the credible set? Sorry, guys. How do I get the credible set? Lower limit and upper limit, and in between with some probability the population proportion. So the graphical representation of the posterior distribution may be this one, from 0 to 1. So how do I find the two values, Q1 and Q2, such that the area under the curve in between is 0.95 or 99? I cannot do by hand. So you have to use the function in R. The function is called Q beta. To use Q beta function, this Q beta function will give me the lower limit and upper limit of the credible set. And I can say with probability 95, the population proportion is between these two values. This is how I get the credible set, but in frequency approach, you use a formula. So what about testing? Testing in Bayesian approach, we use the posterior distribution again, because the posterior distribution has all the information we have. So how do I test H0? Pi is greater than 0.2 versus H1, pi is less than 0.2. We do not calculate p-value, we calculate the probability of H0 given we know y, and the probability of H1 given we collected data, or using the posterior distribution. So you calculate this probability using the posterior distribution, calculate this probability using posterior distribution. So how do I calculate the probability using function p beta? P beta gave me the probability or the area under the curve under some specific value. And you see, I can divide the range, the whole range of the parameter from 0 to 1 into two parts, greater than 0.2 and less than 0.2. This one is 0.2. This area is the probability less than, or the area under the curve less than 0.2. This one is the probability of H1. And this one will be the probability of H0. H0 given y. I forgot to write given y, given we collect the data. So, and you compare these two probabilities and take your decision. Like if the probability of H0 is big compared to probability of H1, you go with the probability of H0. If the probability of H1 is big compared to probability of H0, you go with the probability of H1, and so on. Based on which one has higher probability, you take your decision. So we take decision in Bayesian approach based on probabilities. But in frequency approach, we take decision based on the p-value. And also is not in testing in Bayesian approach, we do not only compare the probability of H1 and probability of H0 given y, we also calculate something called Bayes factor. Calculate something called Bayes factor. This Bayes factor is the posterior odds divided by the prior odds. So what is the posterior odds? Posterior odds I use the posterior distribution. Prior odds I use the prior distribution. To calculate what? Calculate the posterior odds by calculating the probability of H1 given y divided probability of H0 given y, the ones we have just calculated. So you calculate the probability of H1, probability of H0 using the posterior distribution. Do the same thing, but using the prior distribution only before we could multiply by the likelihood. Calculate the probability of H1 before you collect data, divide by the probability of H0 before you collect data. And then you divide the posterior odds by the prior odds, you get something called Bayes factor. So if Bayes factor is 1, it means your confident or your probability about H1 relative to H0, it didn't change after I collect data. But if the Bayes factor is greater than 1, it means the probability of H1 relative to H0 increased after I collect data relative to the probability of H1 relative to H0 before you collect data. And Bayes factor is less than 1. It means the probability of H1 relative to H0 after we collect data decreased compared to the probability of H1 relative to H0 based on only the prior distribution. Because we start by the prior distribution and then we update the prior distribution by the likelihood. So the prior odds is the probability of H1 prior relative to H0 before we collect data. And the posterior odds is the probability of H1 relative to H0 after we collect data, after we update the prior by the likelihood. And then the ratio gave me information about did it change it or not. The probability of H1 relative to H0 changed after I collect data compared to before I collect data or not. So this is why people, when they publish paper about Bayesian approach or Bayesian statistics, they should report the Bayes factor. Any questions so far? Any questions so far? Okay. In Unit 5, in this one we covered prediction, because Bayesian approach and frequency approach are different in prediction, and we covered some other non-informative prior. So, and we drove the posterior predictive probability, posterior predictive probability. And we found that the probability of Y star, obtaining Y star when we select a future sample size, sample of size N star, given that we already did a previous study or previous, the current one actually, given that we selected a current sample of size N and we find Y successes. So what is the probability of Y star given Y, the current one? This one equal N star, the future sample size, choose Y star, the number of successes in this future sample size times the gamma alpha posterior plus beta posterior divided by gamma alpha posterior divided by beta posterior. So everything based on the posterior distribution times gamma Y star plus alpha posterior times gamma N star minus Y star plus beta posterior divided by gamma alpha posterior plus beta posterior plus N star. I know the formula is big, but I do not ask you to memorize any formula. So if you have N star, if I said I'm going to select a sample, I didn't select it yet. I'm going to select a sample of size N star. what is the probability that I will find y star number of successes? Given that my posterior distribution has alpha star equal or alpha posterior equal, beta posterior equal. Can you calculate the probability of y star given y? You can calculate using this one. But in R, there is a function actually is called P beta P. This one actually calculates this probability. So, but this function in a library called learn Bayes. So you need to run this one first. So again, there are, and we covered some non-informative prior. We covered the HES. We covered, we covered some other stuff like improper and proper. Improper and proper priors. How do I know the prior is proper or improper? So, and why I'm interested in this one? Because if you use proper prior, for sure you will get proper posterior. So what does it mean, proper posterior? It means I can calculate the posterior mean, posterior mode, posterior variance, posterior standard deviation. Those guys have some formulas. I can calculate them. But if you use the improper prior, maybe yes, maybe no. Maybe you get improper posterior. If you got improper posterior, it means it is not density function and there is no formula for estimating the population proportion using posterior mean, posterior mode. There are no formulas for these ones, for these characteristics. So you need to make sure that the prior you use is proper prior. So what do you mean by proper prior? It means if you took the integral over the whole range of the prior distribution with respect to pi, this integral should be less than infinity, or it is equal some constant. It's not infinity. So in this case, it is proper. But if the integral over the whole range of pi is infinity or unknown values, this one is improper. You should be very careful when you work with this improper prior. You need to make sure that the posterior is proper. So you can estimate the population proportion by the posterior mean, posterior mode, or you can do credible set, or you can find the probability which is zero, probability which one, using the posterior distribution. But if the posterior distribution is improper, you cannot do anything with this one. Guys, I'm done. Any questions? Any questions? Okay, if you do not have any question, so I have to say thank you and see you on the exam. Thank you. Have a good day. I see no one leave the Zoom. Okay. See you on the exam. Have a good day.